Take a moment, if you will, to consider an object you have kept for a very long time. Perhaps it is a faded photograph of a great-grandmother you never met, stored in a box where the air smells of old paper and dust. Or perhaps it is a silver spoon passed down through generations, its surface cool and heavy in your palm, though its once bright shine is now hidden beneath a layer of tarnish. When we look at these things, we feel a strange, slightly melancholic tension. We know that the molecules making up the photograph are brittle and yellowing, destined to crumble. The silver is slowly being worn away by the mere friction of existing in the world. Even a smooth stone picked up on a beach years ago is slowly being ground into dust by the silent passage of time. We are taught that life is different, that we are composed of meat and bone and perhaps a mysterious thing called a soul, yet we, too, fade. Our cells are replaced, our memories slip away, and eventually, the physical structure we call us ceases to function. But what if I told you that the most essential part of you isn't the carbon or the water or the skin? What if I told you that you are a part of something that has been computing for 4 billion years, and that the secret to your existence isn't found in biology, but in an invisible logic that has outlasted every mountain and every sea? We are standing at the edge of a profound realization about the nature of being alive. We aren't just chemical accidents. We are living computers. I want to invite you to sit with a thought that challenges our most basic definition of what it means to be a person. It is a realization that suggests the answer to the mystery of life is not found in the flesh, but in the realm of the eternal code. For a long time, we have been stuck in a profound biological misunderstanding. We have been taught to see life through the lens of Aristotle, who believed the difference between a stone and a bird was a soul. He imagined different levels of this essence: a nutritive soul for plants, a perceptive soul for animals, and a rational soul unique to humans. When that didn't quite explain the mechanical reality of the world, we turned to chemistry. We looked at microbes through our microscopes and saw them as tiny, complex machines made of clockwork and steam. But as Alvis Brasma explores in his work on living computers, there's one big idea that changes everything. Life is at its core an information processing phenomenon. This is a difficult thought to hold. It feels cold at first, perhaps even robotic or mechanical, to think of our thoughts and our heritage as mere data. But Brasma suggests a deep, intrinsic link that is actually quite beautiful. There is no life without information, and arguably, there is no information without life. If you take away the information in your DNA, you aren't just a simpler organism. You aren't alive at all. Every cell in your body is recording, communicating, and processing signals. Even evolution itself is not just a blind struggle. It is a Darwinian algorithm processing the entire collection of DNA on Earth as if it were a massive planetary-scale computation. To truly understand this living computer, we have to move past the meat and look at the logic of the self, the rules that allow a machine to do something no hammer or lathe has ever done: clone itself. To understand how a machine can reproduce, we have to look back at the history of our own mechanical curiosity. In the 18th century, a French weaver named Basile Bouchin built a loom that could follow instructions encoded on a perforated paper tape. This was the first time we realized that a machine's behavior could be separated from its physical parts. Later, in the mid-19th century, Charles Babbage designed his difference engine 2, a brass marvel of 25,000 parts that had to be manufactured with precision of a fine watch. It weighed several tons and stood as a testament to the sheer difficulty of mechanical computation. Babbage's later project, the analytical engine, was even more ambitious, a truly programmable computer made of cogwheels. But even these masterpieces of engineering suffered from what the mathematician John von Neumann called the degenerative trend. In the late 1940s, von Neumann sat down to solve a riddle. How can a machine build a copy of itself that is just as complex as the original? Usually, when a machine builds something, that something is simpler than its creator. A hammer doesn't make a hammer. It merely hits a nail. A lathe can shape a part, but that part is always a component, never a whole lathe. This is a degenerative trend, the idea that complexity should always leak away into the environment. If this were the only rule of the universe, life would have stayed as simple as a single molecule, forever degrading until it vanished. Von Neumann found the logic of the self by realizing that a self-reproducing system needs a specific architecture to break this trend. He proposed a machine with 8 elementary parts that would allow it to function in a container of spare parts. These included a stimulus producer to create pulses of signals, a rigid member to act as a frame, and 3 organs that acted as logical gates: the coincidence organ, the stimuli organ, and the inhibitory organ. These are what we would call and not gates today. To these, he added a fusing organ to solder parts together, a cutting organ to unsolder them, and a muscle to move them. But the real breakthrough was how these parts were organized into 3 functional units: the universal constructor, the code replicator, and the controller. The universal constructor, which he called U, is a general-purpose robot that can build anything, provided it has the right instructions. The code replicator, or R, does only one thing. It copies the instruction manual. And the controller, C, manages the whole process. This is the secret of life. There is a tape, which we now know as DNA, that contains the instructions. The controller runs a replicator first to make a copy of the tape. Then, it runs a constructor to build a new machine based on those instructions. Finally, it cuts the new object loose, handing it the copy of the manual. By separating the instruction manual from the machine, von Neumann showed why a crystal is not truly alive. A crystal grows by repeating a simple pattern, which Maynard Smith and Safmary called limited heritability. It can't learn. It can only repeat itself, like a book that only contains the same word over and over. A living organism, however, has unlimited heritability. It can carry any amount of information, the blueprints for a wing, a heart, or a human brain. It can carry 4 billion years of survival strategies. This logic is so powerful that it even works in abstract worlds. John Conway's Game of Life showed that simple rules, where a cell lives or dies based on how many neighbors it has, can create gliders that move across a grid or glider guns that shoot out patterns indefinitely. But to make a structure in this game that actually clones itself using von Neumann's logic, you would need a configuration of roughly 10 to the power of 13 cells. If each cell were a millimeter wide, that machine would be 3 kilometers long. It is a sobering reminder that while the logic of life is simple, the implementation of that logic is a staggering engineering feat. This is where the math of information meets the psychology of our daily existence. Information is defined as a reduction of uncertainty. Each bit is a yes or no answer that clears a path through the chaos. In your DNA, the nucleotides A, T, G, and C each carry exactly 2 bits of information. Because there are 8 bits in a byte, every 4 letters of your genetic code represent 1 byte of data. Through the Darwinian algorithm, life learns from its environment. It records what works and deletes what doesn't, slowly reducing the uncertainty of survival over eons. But what happens when this information, which has been locked in the slow, grinding gears of DNA for billions of years, suddenly finds a new home? We are currently living through the most significant event since the dawn of biology, the Great Information Transition. For 4 billion years, almost all the durable information on Earth was kept in polymer molecules. It was a glacial process. If a species needed to learn how to survive a cold winter, it took thousands of generations for that knowledge to be hard-coded into the genome. But a few 100,000 years ago, human language emerged. This was a major transition, a shift as profound as the emergence of the first cell. For the first time, information began accumulating outside of DNA. We created what we call a Neotype, a cultural memory. Instead of waiting for a genetic mutation to tell us how to build a fire or navigate by the stars, we could simply tell each other. We moved from the slow genetic algorithm to the fast cultural evolution of libraries and, eventually, silicon computer clouds. Think of your biological inheritance as your startup capital, the basic biological machinery you were born with. But your cultural Neotype is the wealth you actually build throughout your life. Today, there is likely more information in our digital clouds than in all the genomes of every species on Earth combined. We are the first replicators that can consciously choose which Neotypes to pass on. This shift changes our very sense of freedom. We are no longer just vehicles for our DNA. We are the guardians of a new kind of information stream. But with this freedom comes a new kind of anxiety. We often feel overwhelmed by the noise of the modern world, the endless digital signals competing for our attention. However, if living means processing information, then the quality of our life is determined entirely by what we choose to process. In biology, there is a concept called niche construction. Organisms don't just sit in an environment, they build it. A beaver builds a dam. A bird builds a nest. They create an environment that supports their growth rather than just their survival. In a modern sense, we must practice our own niche construction. We must curate our information environment with the same care a cell uses to protect its nucleus. If you are a living computer, what code are you allowing into your system? Are you filling your memory with the noise of the crowd, or with information that reduces the uncertainty of who you are and what you are meant to do? We must remember that while our DNA is indispensable, if it were corrupted, we would simply cease to exist. Our cultural information is where our true agency lies. We are the first beings on this planet that can choose to pass on wisdom instead of just data. As we look toward the end, I want to leave you with a reflection on our place in the cosmos. In the epilogue of his work, Brasmer reflects on a time far beyond our own, when the sun will eventually cease to exist and the earth will grow cold. It is a sobering thought, but one filled with a strange, grounded hope. If life is fundamentally information processing, then the particular substance that holds that information, whether it is carbon-based DNA, silicon-based chips, or something we have yet to imagine, becomes secondary. We are part of a 4-billion-year-old computation that is only just beginning to understand its own source code. We are the universe's way of remembering itself. Being a living computer doesn't make us less human. It makes us a miracle of logic and matter entwined. We are the guardians of flame that has survived the cooling of the earth, the shifting of continents, and the rise and fall of countless species. That flame is made not of fire, but of bits and meaning. As you move forward into a future where the lines between biological and digital information continue to blur, do not feel lost in the machinery. You are a participant in the most sophisticated process the universe has ever devised. You are the interpreter. You are the code. You are the living record of everything that has ever survived the long silence of the stars. Life is the universe's long-term memory.